So in this activity, they're asking you to determine how many diagonals there are in these polygons. So diagonal is a segment that connects two vertices that are not already connected to sides. So DE, for example, EF are sides, where DF is not a side. So I can draw a segment connecting these two vertices, and that would be considered a diagonal. So, for example, this vertex here and the one across from here, those are not connected as sides. So therefore, that segment becomes a diagonal, and I can connect these 2 points here as well with a segment. Again, that becomes a diagonal. So this quadrilateral has a total of 2 diagonals. So if you go ahead and look at the other 3 shapes and draw in all of the diagonals that are possible, and then turn the video back on when you're finished. So the first shape is another example of a quadrilateral. So the first and second shapes both have 4 sides, and they actually have also 2 diagonals. So in the third shape, these 2 points are already connected, but these 2 are not, so that would be a diagonal. If I draw it from here to here, they're not already connected. But if I draw from here to here, they are connected. So that would be 2 diagonals. The top here, I can connect those 2 points and these 2 points. Makes 4. And that would make 5. So hopefully in this pentagon, hopefully you found 5 diagonals. One thing you'll notice is that for each diagonal from a vertex, there's 1 diagonal coming from each vertex here. That's the same thing here. But here we have 2 vertices coming from each, or 2 diagonals coming from each vertex. So that can be helpful. So that might come over this shape here. These 2 are already connected, but these 2 are not. These are not connected yet. That's the second diagonal. That's the third diagonal. That's the fourth diagonal. That's the fifth diagonal. And then these 2 are already connected. So from this one point, I can draw 5 diagonals. So if I rotate clockwise, I should be able to put in up to 5. Sometimes the diagonal may be already there. That's 3, 4, 5. So we're up to 10 now. Here, for example, I see 1 diagonal coming off. So each of the vertices, I notice there's 1, 2, 3, 4, 5. 5 diagonals coming off each vertex. So this one here still has 3 more that can be drawn. That would be the first. That's the second. And that's the third. This one here I count 3 as well, so that means there's still 2 more. And this one has 4, so that means there's 1 more. Now this one has 5, and this one has 5. So all the vertices have 5 diagonals coming off of them. So that would be a total of 20 diagonals that we drew all together. So one of the, actually 2 definitions that are introduced in this lesson are convex polygons and concave polygons. And diagonals are one of the things that they connect with those shapes. So if you have a convex polygon, which means all the angles inside the polygon are less than 180 degrees, every diagonal will be inside of it. But if you have a concave polygon, that means that somewhere inside that shape, there's at least one reflex angle. Anytime we have a shape in which there's a reflex angle on the inside of the shape, that means that the shape has been The shape will have at least one diagonal that goes up to the outside. So if you see, like here, I have two reflex angles. Notice there's two diagonals. Here, there's two reflex angles. There's two diagonals on the outside. Here, there's only one reflex angle, so one diagonal on the outside. So, so every polygon with a reflex angle, we're going to call concave, and for every reflex angle on the inside, that tells you how many diagonals should be on the outside. So in lesson 1.3, we were talking about definitions, and one of the definitions you were asked to do was a square, and I also added into that conversation a rectangle or rhombus. And the reason why I did that is because the square definition has to have the name of the shape, which is a quadrilateral, and then it has to have two characteristics, two things that differentiates it from all the other quadrilaterals. It has to have right angles, and it has to have equal sides. If it only has one of those things, say for example the four right angles, that square is actually going to end up being in the rectangle family, because rectangles have four right angles. And if I ignore the right angles and just talk about the four equal sides, then that square gets put into the family with the rhombus, because all rhombuses have four equal sides. You have to have both pieces to be able to say that the only shape you're going to get is a square. Well, in this next discussion, you're going to find that you have an equilateral and an equal angular polygon. Those are two very different things in terms of what we're looking at. But when we get to that regular polygon, you're going to find that regular polygon is acting a little bit like that square in our earlier discussion, is that it has to have multiple pieces of information to be able to say this is a regular polygon, just like you need equal sides and equal angles to be able to call that a square a square. So go ahead and look at the picture to the right and decide, based on the way the definition started, how would you finish it based on the pictures. And then when you're finished with the definitions, turn the video back on. So hopefully with the equilateral polygon, you notice that all the shapes given to the right, that they're all equal. All the sides are equal to each other. And with the equal angular polygon, hopefully you notice that all the angles in each polygon are equal to each other. For a regular polygon, this is kind of going along with that square idea. You notice that all the sides and all the angles are equal. So what goes in here is basically both things. Both statements come in here. So it is a polygon that has all equal sides and all equal angles. So when identifying shapes that are perpendiculars and parallel lines, what we have to do is look for specific symbolism. So for example, anytime you see a right angle symbol, which would be like a little square in a corner, that's an indication that those two lines that are intersecting are perpendicular to each other. Even though at angle K they look like right angles, same thing with Q and M, even though they look like right angles, without either a 90-degree angle marking or a little square in a corner, we assume that the angles are not 90 degrees. So it says which pair of angles are perpendicular, or which pair of lines are perpendicular, and that would be, again, when we name a line, we name it with two letters. So using the line symbol on top, JK would be one of those lines that's forming this intersection. So line JK, and the other line going the other direction that makes that right angle is angle JM. Which lines are parallel? What we're looking for are arrowheads, basically. So we use arrows, and not the arrows at the end of the lines, but the arrows somewhere else other than the end. We use those arrowheads to indicate that these lines are parallel. So the parallel lines would be line AB or BA and line CD. And then the last one is looking for a pair of triangles that are congruent. So when I look at this one here, these two, I see a a 1, 2, 3 in terms of tick marks. Here I see a 3, 3, 2 in terms of side tick marks. So they're not marked the same. If I go over here, I see 1, 2, 3 again. And this is a 1, 2, 3. So I'm looking at these two triangles here. Potentially are going to be the congruent triangles because their sides are marked the same. In terms of angles, we've got double, triples, and singles. So the three angles are also shared. So these are the two triangles that are congruent. And so I like to put them in the right order. So our triangle T SU and I'm going to put the letter first where the angles match up. So angle T, which is a double, that gets matched up with Y, which is also a double. And then S, which is a single, it would get matched up with X, that's marked as a single, and then Z. So that would be the pair of triangles that are congruent, and also making sure that the orientation is correct. So again, as you could call it, he called this superimposing one shape on top of another. In the drawing measuring handout, we talked about ways of identifying triangle by angle names, and it's always based on the largest angle. So a right triangle is a triangle that has one angle measured 90 degrees. That would be the largest angle in that triangle. So go ahead and think about how you would end the definitions for acute and obtuse. Keep in mind that we define triangles based on their largest angle measure. So we don't really care about the other two, just the largest one. And the largest one defines the triangle. When you're finished, turn the video back on. So this one here, it's a triangle that has, and again, there's more than one way to end this. The most, I guess, universal or popular way of ending it is that the triangle only has acute angles. That would guarantee that, if I say only acute angles, that guarantees that the large angle would be an acute angle. And obtuse triangle is a triangle that has one obtuse angle. So this ending would be very similar to the right triangle because and we haven't got into the rules about angle measures for triangles yet. But for right now, just understand that if I have an obtuse angle, that's going to be an obtuse triangle. So the last set of definitions involving triangles is about lengths. So for angle names, we looked at the largest angle. For side names, we're looking at the number of equal sides. So take a look at the pictures and try to decide how many equal sides there are, and identify that, and then turn the video back on when you're done. So for scaling triangles, I hope you notice that all of the sides are different lengths. So scaling triangles has 0 equal sides, or you could say have. If you want to change the verb here, you could also say have no equal sides. So whichever way you want to do that. Has 0 equal sides, or have no equal sides. Isosceles triangles, these have two equal sides. This one has 2 equal sides. This one here has 2 equal sides, and this one has 3 equal sides. So that's why the phrase "at least" is important here. So it has to have at least 2 equal sides. We call it an isosceles triangle. For equilateral triangles, all the sides are marked the same here, and all the sides are marked the same here. So for equilateral, the shape has 3 equal sides. The last screen is problems for you to work on. Keep in mind that when you're sketching something, it's not necessarily an accurate construction, but try to make sure you get the lengths as equal as possible. Make the angles as close to right as possible.